this learning module, we'll verify the Stokes theorem for a particular example, for a particular vector field V. So by no means is this a proof of the Stokes theorem. It's merely an illustrative example. So what does Stokes theorem say? Uh, the flux of the curl of a vector field V on a surface is equal to the line integral of the vector field V along the boundary, the closed boundary of the surface. So as you can see from the diagram, we have several surfaces. In particular, we have a blue spherical surface, a hemisphere, and a green circle, and they're both bounded by the black circular shape here. So what I would like to show in particular in this, we'll compute three different integrals. So we'll first compute the curl of V along the blue surface. And as per Stokes theorem, this is going to be equal to V dot dl on the black circle. Because the blue hemisphere is bounded by the black circle. So already here we have to talk about orientation. So the orientation I would pick would be the outward normal for the blue hemisphere, which means the orientation here would be in the counterclockwise direction when viewed from the top here. So it's incidentally the way I have drawn it. This is my x-axis. This is my, I can do better, I think. This is my y-axis, and this is the z-axis. Okay, so the orientation for the boundary is along this path. So, but on the other hand, the black circle also bounds the green surface. So this too must be true for the green surface. And once again, the orientation consistent with this would be dA here. This, of course, is my dl. So we'll explicitly verify that these three integrals are exactly the same. I will use the spherical coordinate system for the first two integrals and the cylindrical coordinate system for the green surface. The particular vector field that I'm going to choose is y(ex) minus x(ey) plus v0 ez. Here v0 is a constant. I'm using unit vector fields that are standard some books and some people prefer EX, others might use I hat. Griffiths, for example, in his Electrodynamics textbook, uses X hat. We should be able to freely move through these notations. Similar remarks apply to EY and EZ, or IJK, or X hat, Y hat, Z hat. It's a quick check that in Cartesian coordinates, and you should check this, the curl of V is minus 2 k hat. Already I'm using k hat here versus EZ, but you should know by now that they are exactly the same object. Okay, so let's try to start actually computing um, integrals. So let me begin by computing the curl, curl along the blue surface in the spherical coordinate system. To do this, first I must have the area vector. Let's recall in the spherical coordinate system, the differential line element is given by dr er plus r d theta e theta plus r sine theta d phi e phi, or the differential area element will have, if we're talking about the radial component, it'll have r squared sine theta d theta d phi. Where do we get that from? By looking at this and these two coefficients and multiplying those two rectangular lengths, if you will, because it's perpendicular to ER. Remember, area is always a area vector is normal to the surface. Okay. In fact, there'll be other components in general, not for our surface. So, for example, for the E theta component, we would have R sine theta d phi, R sine theta d phi dr in the E theta direction. And if you want in the E phi direction, we would have R dr d theta in the E phi direction. But for our particular surface, S, if you will, dr is 0 for the hemisphere. So over here, dr is 0. So dA, if I may use this notation for the particular surface, is nothing more than r squared sine theta d theta d phi. So when you come back to the integral here, I will have, well, the phi integral and the theta integral, and curl of v, which is minus 2 k hat, dot, this is er for the surface, so it's going to have my er vector and its component, if you will, r squared sine theta d theta d phi. So phi would go from 0 to 2 pi as usual. This is my phi. And theta is just a hemisphere, so it goes to pi over 2. What do I mean by that? This is just pi over 2. So once we can work this dot product out, we're in business. If you recall, in the spherical coordinate system, ER is equal to sine theta cosine phi I hat, see now I'm using I hat, plus sine theta sine phi j hat plus cosine theta k hat. And therefore, it's easily seen that ER dot k hat is simply cosine theta. So then, coming back to this Stokes Theorem integral, the area integral, we get del cross V dot dA is equal to, I can bring, for the hemisphere r is a constant, I can bring the minus r squared outside, and then I would have 0 to 2 pi, 0 to pi over 2, 2 sine theta cosine theta d theta d phi, and I can do the phi integral already. There's no phi here, so integral of d phi from 0 to 2 pi is just 2 pi, so I get minus 2 pi r squared, 0 to pi over 2. 2 times sine theta cosine theta is sine 2 theta d theta, and the integral of sine 2 theta is minus cosine theta over 2, so I can cancel the minus off. Cosine 2 theta over 2 from 0 to pi over 2, and that's equal to, the 2's would cancel here, so I would get pi r squared cosine pi minus cosine of 0. Well, this is minus 1 and this is 1, so minus 1 minus 1, it's minus 2, and I'll get minus 2 pi r squared. And this is the result we want. This is the first integral, and what we will do is we'll verify that the other two integrals yield exactly the same result. So now, next we'll try to compute the line integral, this one right here, along the circular path. So let's do exactly that. So integral of v dot dl, the closed integral, it's a closed circle. This is a black circle, just to be clear. And this is going to be v, so let me write out, what is it, y ex minus x ey plus v0 ez dot dl. Once again, the differential line element is nothing more than dr er plus r d theta, e theta plus r sine theta d phi e phi. Now, for this circular path over here, dr is 0, and so is d theta. So dl for us, practically, for the line, well, the circle, is r sine theta d phi e phi. So we can come over here and continue our integral. When I do this, let me go ahead and write out the expression for y and x in spherical coordinates. So y, if you recall, is r sine theta sine phi, sine theta sine phi Ex minus R sine theta cosine phi for x, Ey plus V0 Ez, and the whole thing dotted with E phi, and the factor here is R sine theta d phi. If you recall, E phi can be written just in terms of Ex and Ey. It's minus sine phi Ex plus cosine phi Ey. So now we're able to take these dot products. When we take these dot products, we'll simplify further because over the entire line, the circle here, this is theta equals pi over 2, which implies that sine theta reduces to 1. So I have R sine phi, but then I have Ex dot E phi, which is a minus sine phi. Minus sine phi. Then I have minus R sine theta, which is 1. Cosine phi. So cosine phi. And then I have Ey dot E phi, which is another cosine phi. So this is another cosine phi. This dot product is simply 0. So I would have this R sine theta, which is again 1, d phi. This is 0 to 2 pi. I suppose we should go back and put 2 pi's here as well. So let me factor out the minus sign and an r squared. So I get minus r squared, 0 to 2 pi, and then I have sine squared phi plus cosine squared phi d phi, but from Pythagorean theorem this is simply 1, so it's the integral of 1 d phi from 0 to 2 pi, and so we get minus 2 pi r squared, which is exactly what we had for the curl of V on the blue surface. So the two terms in the Stokes theorem actually does match as expected. But as I mentioned before, there's another surface here. This should yield the surface should yield the same answer as well. So let us go ahead and verify, compute the integral for this surface. Meaning, what do I mean by that? I mean precisely this: curl cross V, or del cross V dot dA for the green surface. Okay, this is an area integral, so, and like I said, I'm going to use cylindrical coordinate system here. So let me begin by writing the differential line element. I like to compute the differential area element from this. It's an easy way to remember. And Griffiths uses S instead of R. Some authors prefer to use R. Frankly speaking, I do as well. Oh, this is not I hat, but rather S hat. It's like the R hat, if you will. This is d phi, phi hat, and dz, z hat. So the differential area element, if I wanted the S hat component, I would multiply these two guys. So it's S d phi dz, plus if I wanted the phi hat component, I would multiply these two guys. So I would get ds dz, plus if I wanted the z hat component, and I do, I would get s d phi ds. The d phi and ds is perpendicular to z hat. Why do I need the z hat component? Because this now is my differential area element. Okay, so for the surface, once again, we could even simplify the differential area vector with this notation. For this green surface, uh, we find that dz is 0. It's in fact the z equals 0 plane. So already you can see this is nothing more than s d phi ds. So once again, I would have two integrals. Curl of v is minus 2 k hat dot z hat s ds d phi. And look at my notation here. This is exactly the same thing. So it's 1 unit vector. Phi, as always, goes from 0 to 2 pi. And this s goes from 0 to the radius of the circle, which is r. So I would get minus 2. I can bring it out. Let me very quick. This is fairly simple. Let me do the phi integral. It's another 2 pi. And this is 0 to r. S ds, well, that's minus 4 pi. S squared over 2 from 0 to r. And this is easily seen to be, the 2's would cancel, minus 2 pi r squared. And this is exactly the number we generated the other 2 times, thereby verifying the Stokes theorem for the various surfaces and its boundaries. Oh, boundary in this case, just a black circle. Now, if we had, in general, suppose we had a more complicated surface. If I wanted to be really mean in class and I gave you a complicated surface that sort of looks like this and asked you to compute the integral along the surface, this would be very difficult to do. You have to do it numerically. It would be far too complicated. Or realize that it doesn't matter what surface we're talking about, it's bounded by the black line. So you could simply compute the v dot dl along its boundary and it'll give you the same answer. Hopefully this module has been helpful in clarifying the utility of Stokes theorem and also how to carry it out. And this concludes this learning module. Thank you.